Previously, we covered the core foundations. Now, in Part 5, we tackle Venus, climate history. Hancha's orbital dispatch. Venus. Episode 5. Climate history. Venus is the hottest planet in the solar system. Not because it's the closest to the Sun, but because of what happened to its atmosphere. Understanding how a world so similar to Earth ended up like this might be the most important question in planetary science right now. In the last episode, we looked at Venus's atmosphere, that crushing, chemically hostile blanket of gases that makes the surface one of the most extreme environments in the solar system. This time, we're going one step further back. The core question is this: how did Venus get here, and was it always this way? That question matters because Venus is almost the same size as Earth, sits in a broadly similar region of the inner solar system, and is almost certainly made of similar raw materials. If it went one way and we went another, we need to understand why. Act 1. Setup. A world that shouldn't be this bad. Venus orbits the Sun at roughly 108 million kilometers, about 72% of Earth's orbital distance. Its diameter is 12,100 kilometers. Its gravity is 90% of Earth's. On paper, it reads like a near twin, but the surface sits at around 465 degrees Celsius on average, with atmospheric pressure 90 times that of Earth at sea level. The atmosphere is 96% carbon dioxide. And here's the thing that keeps climate scientists paying attention. That didn't have to happen. Something changed Venus. The question is when and how fast. Here's the open loop. There is strong evidence that Venus may once have had liquid water on its surface. We'll come back to that. Act 2. Discovery. Reading the record. Venus's geological surface is relatively young in planetary terms, estimated at somewhere between 300 million and 600 million years old. That points to a large-scale resurfacing event, where volcanic activity essentially repaved the planet. Before that event, the surface record is gone. What we do know from modeling and mission data, particularly from ESA's Venus Express, which operated from 2006 to 2014, is that Venus's volcanic history has been central to its climate. Enormous volumes of carbon dioxide were released into the atmosphere over geological time, and without a functioning carbon cycle to draw it back down, it accumulated. The result is a runaway greenhouse effect, one of the clearest examples of that process we know of. Solar radiation gets in. Heat cannot escape. Temperatures climb until they stabilize at a level that would melt lead. Now, back to that open loop about liquid water. Several climate models suggest that early Venus, perhaps 3 or 4 billion years ago, may have had a shallow ocean and temperatures mild enough to support liquid water. That's not confirmed. The evidence is indirect, but it changes how we think about habitability across the solar system. Because if Venus had water and lost it, the same process could, in principle, affect other worlds. Act 3. Implications. What this tells us. The lesson from Venus's climate history isn't just about Venus. It's about thresholds. Earth and Venus started from a similar position. Small differences in distance from the Sun, in volcanic outgassing, in the presence or absence of a magnetic field to protect against atmospheric loss. Any of these could tip a planet from one state to the other. Venus shows us that a terrestrial world can cross that threshold and not come back. That's worth understanding properly. Next time, we look at Venus exploration and the open questions that missions old and new are trying to answer, including why several space agencies are planning to go back. If you found this series useful, subscribing helps the channel keep going. No algorithm tricks, just more of this. The full Venus playlist and the rest of the series is linked in the description. That is part 5 of Venus. In part 6, we explore the next key question. Subscribe so you do not miss it.